All right. Hello again, everybody. My name is Qiyang Hu. I work at the UCLA Office of Advanced Research and Computing. Today, I would like to talk about a very powerful and cool Python library named Scikit-Learn. So please feel free to let me know if you have any questions and type your questions in meeting chat. So actually, this is one of my talks for talking about Scikit-Learn. So in this quarter, I would use the 2 sessions to talk about how to use Scikit-Learn. Today, we will talk about the mainly focus on the basics of the Scikit-Learn. So the basic meaning, I will focus on an introduction from a bigger picture viewpoint, mainly from as I shown here, as high-level overview for the basic components or the modules of the Scikit-Learn and what's the code structure that the Scikit-Learn library organized. So I will introduce those different components according to a typical oversimplified machine learning workflow. Also, after the basic introduction for the Scikit-Learn, today I will mention a little bit about the practical usage of Scikit-Learn in the modern days, because I know that many people actually have the questions about what's the relationship between the neural networks and the Scikit-Learn. And also, I will talking about a lot of, in the practical sense, so a lot of third-party or official extension libraries based on the Scikit-Learn. Next week, we will focus on some advanced topic for using Scikit-Learn. So basically, we'll try to focus on some concerns about the performance issues using Scikit-Learn. So we will try to introduce some concept on how to do the very basic fundamental concepts about how to do the high performance machine learning using Scikit-Learn in the next Friday. I know all of you come from different fields with a different level of experience. So before I dive into the details, I want to make sure that we are on the same page. So here's what you can expect from this workshop and what I hope you will get out of it. So the first those my talks will focus on the review based on the machine learning workflows. I cannot and I don't have the time and enough slides to introduce the various mathematical machine learning models. And also, even for the Scikit-Learn itself, it contains tons of features, functions, and components. So can only skim over the all those features, the functions, the components. So that's what I said. I will focus on the big picture. So, but for the details of specific like function interfaces, arguments, parameters, even hyperparameters, I think I will leave out of that, out of my talk. And come with my slides. So I actually prepared a couple of demos, let's say, mainly in the Colab notebooks. So all those demos are actually some examples that I copied from some documentations or somewhere else or written by myself. So I'm just, I think that the 2 hours or 4 hours talk about Scikit-Learn, I don't have time to make the line by line explanation. So probably if you are interested in some part of the code, you probably need to study after the class and then maybe refer to some documentations. And it's specifically for the next talk on advanced usage about the Scikit-Learn, I can only make a high-level introduction on the high performance issues during the machine learning using Scikit-Learn. For the details and mechanisms and implementations, that will be a really deep topic. So if you guys are interested in any of that, please feel free to give us some feedback, either from the survey after the session, and let us know, and so that I can prepare the special topics on what you are interested. Okay. So another question is about the large language model recently. Recently, almost everybody feel amazed by the amazing abilities shown from ChatGPT, especially when you use its plugins like a code interpreter recently opened to all the subscribers of the ChatGPT. And many people, including myself, actually believe to some extent that very soon, the more large language models can do more things that as a data analyst or system admin or code developers are currently doing. But however, I think at least for now, we still need to learn either Python or Scikit-Learn in a basic sense, so that we can do a lot of more things like productive nowadays. So here in the slides, I want to make the two main arguments to showing from my mind why learning Scikit-Learn in the large language era is necessary still. So the first is learning Scikit-Learn. It can help us to provide the better and efficient prompts. So that means Scikit-Learn can help us to have a better understanding on machine learning models and concepts. And also learning that kind of knowledge, it can help us to provide more efficient chain of thoughts. And also when we read the response from the ChatGPT or large language models, it can help us to nail down the key problems much quicker on that. And also learning Scikit-Learn can help us to do a lot of things far beyond the zero and few shots from the large language model. We have to admit that the current large language models cannot do everything yet. So not only from GPT-4 or Llama 2 or Lambda, that I haven't seen any like open source uses for the Llama from the Google. So that means even we actually explore a lot of intelligent power from the large language model, so we still need to fix the hallucination problem from our end, from the user end. Also, we need to distill the domain knowledge that actually contained from those gigantic black box. And sometimes it's we need to do something that beyond those zero and few shots. That means we need to fine tune or to do some downstreaming works on those model. Say we want to do something beyond those foundation models to apply our specific knowledge to do the things that we're interested. So I think this is a pretty interesting topic and very hot nowadays. And in today's talk, in the basics talk, we will briefly mention a case, that's a very simple case to use Scikit-Learn combined with the power of, I say, BERT model to doing some simple classification work on that. Okay, so let's learn what is Scikit-Learn in 5 minutes so that we can dive into the details. Scikit-Learn is a Python machine framework. So it is we can understand the Scikit-Learn as a library built on the top of a bunch of popular Python libraries. Say, for example, it uses, inside Scikit-Learn, they actually uses matplotlib and the plotly for plotting, and they use the NumPy for array vectorization. And they also use the pandas data frames, and also SciPy for scientific algorithms, all many more. I think the projects are started in 2007. So as a Google Summer Code project by, I think the name is David Kernable. At that time, they use the name Scikit-Learn, meaning that they look this one at the third-party extension of the SciPy. So that's why they use the Scikit, means the SciPy toolkit. And then the Google Summer Code project became publicly released 3 years later. It's currently maintained by volunteers. So I think it's a form of very thriving international community. I think last time I checked the GitHub, so I think they have over 2,000 contributors for the project. So it's a very big and very good community to maintain the Scikit-Learn. Installing and loading the Scikit-Learn are pretty straightforward. So they have multiple ways for you to use the Scikit-Learn. If we want to running the Scikit-Learn on the local machine, we can install the Conda or Miniconda or Mamba. So all those are, you can simply install Conda, install Scikit-Learn. So usually they will find the package from like a Conda Forge or the other channels that you defined locally in your desktop. For here, I'm actually using a special package that provided from Intel. So that means if your desktop have Intel-based CPU, then it's better. I would recommend that you use this version because this is a specialized compiled by the Intel. So it's Intel. That means Intel actually rewrite many estimators inside for the Scikit-Learn. So I think they were actually have a very good performance. They're using Intel's own like a OneDAL C++ library and optimized a lot, especially for the x86-64 architecture. So if you are using like a Mac or like with a Silicon M1 chipset, I believe that from the very beginning in your Conda installation, you already selected with ARM64 based on that. Then simple Conda install Scikit-Learn will actually provide the optimized version for the Apple M1 Silicon chip. And I think all of us are actually UCLA affiliated persons, so we have an account on Hopin2. Then you can simply load the system module named Anaconda 3. And I think I installed the Scikit-Learn in virtual environment so that you can use the Scikit-Learn directly on the Hopin2. I recently upgraded Scikit-Learn to its latest release, version 1.3.0. So I highly recommend that everybody use this to use the Scikit-Learn 1.3.0 because they have a lot of like very good features upgraded. Specifically for this talk, I'm actually using the Google Colab because there's actually the Jupyter notebook sessions provided from Google Colab come with almost 90% of the data science packages ready, pre-loaded. So that would be the quickest way to use the Scikit-Learn and to learn how to use Scikit-Learn. And I would say that Scikit-Learn is from some open source or volunteer-based project, but I would say that the library is designed for production. So the structure and the logic, the code logic is very simple, and the quality of the code are very good. And I mean the very good meaning, so they have they actually have a very good performance in the sense of using NumPy and SciPy extensively inside the code for high performance linear algebra and array operations, and especially some core algorithms in the Scikit-Learn, they are written in the Python directly to improve the performance. And also the quality, high quality code, what I mean is they have very elegant, neat APIs. I would say that those APIs may not are originated from Scikit-Learn, but Scikit-Learn use those APIs so good that it's become sort of de facto that later many machine learning or deep learning libraries, they actually try to use the similar, they try to provide the same or similar APIs as the Scikit-Learn. You can really see how easy it can be used by just a few lines of code. I believe I copied this code from the documentation page, but you can simply understand the simple logic for the whole Scikit-Learn based approach for the Python code. Let's say in this simple code, we want to do the feature, do the classification for sample of data like this. And in the code, you only need to import the Scikit-Learn. And then in the data part, you just define with the list and the multiple and for the training set and the labels. And for the modeling part from the Scikit-Learn, you can just simply import the specific algorithms or models from some modules, and then you just call those models to form the model for you, and then to run the dot fit to make the modeling part. And then for the prediction stage of the work, you just call the model dot predict. So those are just a very fundamental usage or the template for the Scikit-Learn to use. I want to say that this is one thing for the Scikit-Learn is they have a very, very good documentations. So those Scikit-Learn, scikit-learn.org, I would say that from my personal experience, this is one of the best documentation for some code or for some library usage. So it's everything seems designed very straightforward and very simple, but there's tons of details. And anytime we need we want to know something deeper, we have to go to this documentations. I mean, for myself, I frequently check the documentations. It contains with the elegantly linked with the examples, code, and then some discussion users guide. So that's it's highly recommended. Okay, so are there any questions that you guys have so far? Okay. So, well, this is the simple, very simple introduction for the Scikit-Learn library, and we will dive into some details. I want to say that the Scikit-Learn is a comprehensive, we can understand the Scikit-Learn as a comprehensive collection that covers almost every step in the machine learning workflow. So in this talk, we will introduce the different part of the Scikit-Learn according to this oversimplified workflow for a machine learning project. So let's start it with the first part, that is getting data. Getting data is acquiring data or getting or generate the data for my model, for our model. It's a pretty natural step for the very first step. We in the Scikit-Learn, so by default, they will read from like the NumPy and the array. So actually, but we have to keep in mind that the numpy.ndArray is for the dense data. So that means that the data are regular. We don't expect so much zeros appearing to in the ND-array. That's data. So that's why we call it the dense data. But sometimes we, in a scientific or engineering project, so we have to deal with some data with a lot of zeros. So it's sometimes we need to use the sparse type of the data format. And the good thing for a very powerful thing for the Scikit-Learn is that they can read directly from the sparse matrix format from the SciPy. So so I think this is a very, very powerful point. It's even more powerful than the TensorFlow and the PyTorch. So we will talk about this one, and we will give some comparisons between the Scikit-Learn and the PyTorch and the TensorFlow in the later slides. But I want to point out that by default, or in most cases, we only need to work with the dense data, but then sometimes when we doing with some data that need to be compressed, so then the sparse data will become a very critical point that we need to consider. And getting the data, meaning we can not only so in one case that we got the data from outside, we collect the data, but this, in the learning stage, we need to test our model so that we can get from some like a standard data set to make the test. And the good thing for the Scikit-Learn is that they provided with some preloaded, or they actually come with some standard data sets inside the Scikit-Learn. For example, if the data set is pretty small, and then they call it as the toy data sets. So toy data sets are actually started with a sklearn datasets.load underscore with the different names, with the different various names for those toy datasets. So that load underscore means that we don't have to download any data from external website. So that's because that's pretty small. And if the data set is a little bit bigger, but still the very standard data sets, then they provided with a function like a sklearn.datasets.fetch underscore with a different data set names. So those names are meaning larger, and then it can be whenever we running fetch underscore, so they actually download them if necessary during our session for the Scikit-Learn analysis. I want to say that in a return, the return data that returned from those data are returned by from Python. They call it a bunch object. So the bunch object is basically a dictionary that exposes its keys as attributes. So in this simple example, you can see that if we define a bunch object, so then there will be, we can access the members or the contents inside the dictionary, either by the keys or by the attribute itself. So that's basically just the dictionary-like object that Python dealing with. So in the code, you may have to, by default, they will return the bunch object, but sometimes you have to have some parameters to say what the type of object you want to get from like a training and a testing. So we will see some example code in the later slides. And at the same time, Scikit-Learn include various random sample generators that can be used to build some artificial data sets of controlled or specified size and the complexities. So the Scikit-Learn.datasets.make underscore, those functions provide the different generators for different tasks, like machine learning tasks, including those are from the documentation of the website. So, but they have a specific data generators for the problem of classification and clustering, for regression problems, for the manifold learning problems, and for the decomposition problems. For example, like if you check with the make underscore blob, so the blob in the Scikit-Learn, so they are some isotropic Gaussian blobs for clustering problems, and you can see that they have a lot of like parameters. You can check from their documentations, like how many numbers, how many samples, and how many features you want in the blob, and then you can define where is the center box, a center box, and then like either centered or not, something like that. So those are just a example that we can get some synthesized data if we really want, if we want to test our model or to learning some concepts or learning some algorithms. So those data generator are very handy tool for us to start with. Okay, so let's for this time, let's first jump into some demos first. I think this demo contains a lot of snippet code. By the way, I forgot to mention that we have a GitHub repo for this class, and I will copy this one to the chat. So this actually contains all the materials, including slides and including the video recording and including the demos. So anytime you can just check after the class for all the things that you want to check with. I think at this time right now, so I will open up with the first demo that I formed for this class. So those I named as a Scikit-Learn toy example, so that almost all the codes are copied from the Scikit-Learn documentation site. Before I'm diving to the details of the code, I want to mention that I found, like for myself, Scikit-Learn recent release 1.3.0 are pretty good. So unfortunately, the Google Colab haven't been updated yet. So by default, they installed the Scikit-Learn with 1.2.2, and we need to running this explicitly like a pip install upgrade Scikit-Learn, so that it will be upgraded our Scikit-Learn inside the Colab to the version that we desired. And you can see that they included a lot of the new algorithms, especially the one that I'm pretty interested in is HDB scan. So previously, we have to pip install HDB scan separately from the third party, but right now in the Scikit-Learn version 1.3.0, so they come with HDB scan. That's very good news for me, at least. And also they included with some target encoder for regression and classification targets. And also they have very cool validation curve visualization. So that's you can check all those release highlights by the link here. So you can see that there's I really like this version of the upgrades for the Scikit-Learn. So I'm just giving you the notes before we go over our Colab code. So from here, we will start jump back and forth between the demos and my slides, but I want to just to show you that in this Colab IPython notebook, so you can see there's some example code for, so far we introduced about the data loading part. So for example, you can see the code for loading standard data sets. So for here, I believe I used the example, I copied the example of iris data sets, like the toy model. So you can see that there's some code that showing the data, what it looks like. And also they can load the sample with loading some data from external sources. For here, I'm loading a sample image. We assume, so those are just come with the Scikit-Learn, but we can imagine like we can load some data from outside of that. And also we can fetching larger data sets. For here, I believe this example, I'm using the California housing data. And so for this part, we are fetching some database from OpenML. I think that's related with some gene or mice gene database. So you can see that it's actually, they actually fetching the data on the fly whenever needed to check the data. And then there will be some data generator parts that we mentioned about we can make the data for classification, we can make blobs that we showed in the slides, and also we can generate the Gaussian quantiles data sets on that. So I believe that we don't have enough time for to go over the details. So it just to give you some just scratch the surface on what it looks like on that. Let's jump back to our slides to go to the next part, our testing data and the training data. It's meaning like we need to doing some splitting before pre-processing the data. And so those are very important because we want to have an unbiased evaluation for prediction performance. So for here, unbiased evaluation means that you cannot evaluate the predictive performance of the model with the same data you used for training. So basically, we have to separate the data for the training data and the testing data so that we will actually make sure that we want to evaluate the data with some unseen to the model. I mean to some fresh data that unseen by the model before. Internally in the Scikit-Learn, so they use the cross-validation iterator to split. So how to say that it's an iterator? Iterator, we can understand the iterator as algorithm that it will return you a tuple of training and the testing fold at each iteration. So those are actually it's not a simple task, because depending on different data sets, different splitting schemes or methods or techniques have to be applied. The most common one that might be the stratified splitting. It means that we split the data according to the class labels. Scikit-Learn provide the two modules. One is stratified k-fold, another one is stratified shuffle split. So I think we don't have time to specify what is the shuffle and what is the stratified. If you're interested, maybe we can continue doing some detailed discussion after the class or at the end of the class. But I want to point out that this is a stratified splitting is only one of the splitting methods. if your data were divided by groups on top of the labels, you cannot use the stratified splitting. You have to use some group splitting methods. And also if your data are time sequence data, so that means like so the random permutation of the splitting are not allowed. So then you have to use a special time series splitting method. For example, in the Scikit-Learn, they provide time series splitting method. And of course, for your own data sets, you may need some special splitting. So you can define your splitting method based on some like a base method, or you can predefine some splitting method by yourself on that. What I mean here is that the splitting method are actually very complicated task for the machine learning problems, and we don't have time to dive into the details of those techniques. But in Scikit-Learn, they provided with a very simple wrapper they named the train test split. So we can understand that this train test split is just a simple wrapper for a single call of they call it the shuffle split. So we're talking a lot about the splitting method, because splitting meaning like you may have it means that it's a multiple iterations. That's why they call it the cross validation iterators. So they have to, for example, they have to define with k iterations and doing with the shuffle for each iteration, and then to select one part of the data as the test, another part as the training data, and then to doing the multiple iterations, each iterations, so they can define, they can keep the index so that we can make the evaluation for the model. So that's what we mean the shuffle split. The shuffle split meaning like full of multiple iterations. But for the train test split, it's only a single call, meaning only one step, only one step, one iteration to do the shuffle and then make the split. So that's the simplified understanding of the train test split, what they did. And it's only allowed for stratified splitting. So you cannot, your data or whenever you use the train test split, you cannot, using the data that have the groups on top of labels, you cannot use for the data that the time series have time sequence data. And so that's only for the stratified splitting. And it's as a base for the default cross-validation as I just described. So those are just one single call, one iteration inside the shuffle split. So that's why we call it as the base for the default cross-validation. So in the code sense, that's a very straightforward, I think. So you can just simply call from the scikit-learn.model_selection. So those train test split are in the modules of model selection. So we will talk about those modules in the later slides. But then whenever you call this one, and then you can make the train test split by the function call of train, the training set, and then the labels, and then with the test sites, with giving, say, for example, in this case, we're using 40% of the data as the test, and then we define with the random state. So one minor note that the return xy equals to true, meaning that by default, those data sklearn.datasets.load underscore toy dataset, by default they return as the bunch object. but then return xy equals to true, meaning like we want to get with the separate with the x and the y on that. Okay, so this is just a so it's a simple understanding for the training and test split. I just shuffle and then make the split. So then let's move to the core part of the Scikit-Learn. So those core part include all those 3 steps, major steps in the machine learning. That means the data pre-processing, and then doing the modeling work, and then doing some prediction or doing some evaluation part of the work of the models. And all those are based on a very all come from they call it, I believe that in the Scikit-Learn documentations, they call all those are defined under like a parent class. They call it the estimators. They call these estimators as the core objects. I think from my personal viewpoint, this is the bad name on that, because it's actually confused with the estimator that used in the code. And so that's one of the confusions that in the terminology defined inside the Scikit-Learn. And you can see that in the core, let's not using the estimators. Instead we use the core objects to describe the central piece of the Scikit-Learn. So in the core objects, we have roughly saying like 4 main core objects. One is estimator. So it's a estimator is some function that it's actually provided with some function implement a fit method to learn from data. So basically we want to actually running training and then to learn from the data. To learn meaning like to get the parameters or to get some statistics properties, to get some models parameters from the data. So those are dot fit method. And so if we doing the modeling and learning, we most of us already have the concept that the model and learning, meaning we want to fit the model first based on some training data, and then using those fitted models so we can make the prediction. So, and then doing the prediction is the core project named predictor. So the predictor always provide with dot predict, that kind of a method. And then the third object, they call the model, meaning the model implement the special method named the score to give the goodness or of the fit measure or likelihood of unseen data on that. So there are couple of nitty-gritty details for the predictors predict method. So is, for example, like generally speaking, you just call dot predict, but for classification algorithms, they have their some kind of like a variance on those predict methods. So one is a predict underscore probability, predict underscore prob, or they have another variant is called decision underscore function. But we can generally understand that those one are all predict method. So, and the fitting method is not only for the modeling and learning part, but also happens on the pre-processing part, meaning like whenever we're doing some feature extractions step during the machine learning, the fit method also can help us to calculate some statistical properties from the training data. Those statistical properties include some like mean values or standard deviations in normalization or in some standardization process we may need to get the mean value or maximum value, or in some unsupervised like learning problems, we may need to find the principal components in PCA method, something like that. Then those are actually happened in the model, in the learning, but also in the pre-processing stage. So you can see that sometimes we need to apply the we need to use the fit to calculate the parameters for the training data, and then we use the properties that we already got from those fit method to transform the data so that we can do the modeling part later in the later slides. And then those are actually not only in in those steps, pre-processing step, we need the estimator, core object estimator for fit, and also we need the fourth core object for transformer. They named the transformer. So the transformer is not the thing that we're talking about, that the neural networks are actually to transform the data. So they have a dot transform method. So the transform method is transform for using the calculated parameters, applying the transformation to a particular data set for the pre-processing. So sometimes a little bit confusing is they also provide with the fit transformer dot fit underscore transform. So basically those fit transform are the combination operation for both estimator.fit and the transformer.transform. So it's a little bit tricky concept. But we can simply understand that it's for the training data. So we usually apply the dot fit. I mean, what I'm talking about is a pre-processing. It's not for the model and the learning. So it's for the pre-processing, we need to fit the training data first to get the statistical properties, and then to transform according to the fitting model to get the transform the data. And so those are good for training data. So that's why it's usually we use the fit underscore transform for training data. But it's not good for the testing data, because testing data, we actually want to use the model fitted for the training only. So if you call the fit transform for the testing data, so those are actually doing with some model fitting for the testing data, that's actually violated our unbiased evaluation rule. So that's why usually you can see that it's previously you can see that we can do with the fit transform for the training data. And then after that, whenever we're doing with the test for testing data, we can only call the transform for the testing data. And I think there's some simple code that will make things very clear. So let's move to the workflow that for the data pre-processing step. The Scikit-Learn sklearn.preprocess package provide various common utility functions and the transformer classes to change raw features into a representation. Those representation hopefully is more suitable for the downstream estimators, I mean for the modeling part. So I also just summarize from the documentation of the Scikit-Learn. So those are pre-processing methods include standardization, mean removal, variance scaling, nonlinear transformation, normalization, encoding categorical features, discretization, custom transformation, transformers. All those are under the pre-processing modules. So here I actually copy a piece of code that use the standard scaler. So first we import those special functions. standard scalar, and then we define the scalar as SC. So then for the training data, we can do with the standard scalar, we want to fit the training data using standard scalar, and then to transform the training data. So combination of fit and transform give us maybe sometimes in some cases give us some slightly like a performance benefit for combining those two and the transformer object of the fit and underscore transform. But for the testing data, we cannot call those fit because we don't want to running the fit on the testing data. So we can only running as standard scalar dot those pre-processing method dot transform on that. So there are special or separate name of the modules that actually belongs to the stage of pre-processing work is imputation part. So they can do with some imputation of missing values by simple imputator, iterative imputator, and KN imputator, and missing indicator, all of things. So if you check with some details, keep in mind that the Scikit-Learn.imput did a little bit different compared with the pandas few now values. So impute has to, so whenever we're running the Scikit-Learn.imput, I mean, in the Scikit-Learn impute are actually using the two core objects, including the estimator and the transformer. So that means they actually doing the fit first with a couple of more lines, but they simply mention mean and median to perform some action. But in the pandas few now values, so you just need to provide the values to fill out those now non-available values. So those are quite different operations. So just keep in mind. Other than pre-processing, Scikit-Learn, Scikit-Learn provide other modules for during this stage. For example, like they have a feature underscore extraction, feature selection. So those are just all that kind of for specific like problems. So we will actually use I think in the later slides we will see a demo that using the feature extraction method or like a feature extraction technique specifically for text and images like a tokenization. That kind of I think we use the feature hatching as the feature from the Scikit-Learn.feature extraction module. So we will talk about that in the later slides. But let's say the core part. So everybody talking about machine learning I believe most of us talking about those parts, meaning we want to select one of the machine learning model and doing some loss functions and to try to fit and training the model. I didn't find the better figure to showing the right estimators that we can consider, but this figure are copied from the Scikit-Learn website. That's a documentation site. So those are very rough, very rough guide on how to approach problems with regard to which machine learning model or what we call estimators in Scikit-Learn jargon to try on your data. It's not precise, and also in nowadays the territory might completely different. It's not valid, but it still gives us a very big, roughly correct overview for the whole landscape. For example, like but it also provided us some like a chain of thought to approaching machine learning problems. For example, like we got some data, we need to consider the size of the data, and then we need to see whether it's predicting the category or whether we want to do the supervised or unsupervised, we're doing with classification or regression problems, or we are doing with the and all those like with the testing data, or we want to doing with something that the kernel approximation for all those kind of things. It just for reference. I mean, it's sometimes we as a data analyst, we stuck here like a tough luck. But sometimes, in most cases, right now, it's all like we can follow some route and to get the appropriate solutions for our problem. So it just so now I think this one are related with the machine learning topic, that it's what models can do, what kind of tasks on that. But in the code sense, whenever we're learning scikit-learn, we have to know one thing, that in scikit-learn organize the different models in a way that they actually put the different models or specific models under some different modules. So the machine learning model under different modules. So different module names just represent different category of machine learning algorithms. Say they have a linear model, they have a supervector machine model, they have tree, naive Bayes, multi-output, ensemble, cluster, decomposition. All those are just the one category of the specific model. So what we can do is to know our problems according to those map that in the previous slides possibly, or any other some thoughts, and then we target some specific model that we need or we want to use for our problem, and then we found which model that the model under what kind of modules from the scikit-learn. So then we call with the from scikit-learn.linear model import. In example, for example, I want to do it with logistic regression. Then from this one, we call this, and then we define our model by the specific model name with all hyperparameters. Let's say the penalty, tolerance. I mean, those I use the example of logistic regression. We can define with the maximum iteration steps and using what kind of solver, like it's, for example, by default, they use liblinear.so and how many job or workers to running that. Some are actually have the multiple threads available, some are not. And then by defining the model, then we can do the fit method to fit the data, and then we can do the predict, and then we can get the score. So all those are actually come back to our learning scikit-learn in 5 minutes, so that it's actually almost every step are follow this template on that. All those modules are related with except, for example, in this logistic regression, we have all those hyperparameter in the parameter list. But there is a very special module that we call ensemble. So ensemble is sort of a very special type of estimator that I want to specifically list it here, because other estimators that sometimes we call other than all the models, other than the meta estimators or ensemble estimators. Those are usually we call it as base models. So those base models usually only accept the hyperparameters in their parameter list. but a meta estimator is a model that basically assemble a group of base estimators. So a simple understanding of that, it would be they can accept the base model names in their parameter list. So basically you can see that it would be on the top of the base models. So they can accept the base model names as a parameter so that they can running everything together in an organized way. And I'm just checking with the documentation. So those are some list, or I can have a brief overview on what it contains in the meta estimator. So we can have ensemble, multi-class, multi-output, model selection, pipeline. All those are the modules that belongs to meta estimator. So those are ensemble or multi-output data. That's what we call it in the previous slides are the meta estimator. And you can see that it's they contain a large number of the famous algorithms that we might use. For example, like in the previous slides, we used the train test split that actually belongs to the model selection module. So model selection module are one type of meta estimators. And also those, for example, like we use the boosting or average boosting methods are actually, for example, like want to use the random forest classifiers. So those belongs to the ensemble estimators like Scikit-Learn dot ensemble dot that random forest regressors. So we don't have time to go over all those details on that. But let's jump back to our code so that you may have just some impression or feeling about what it looks like. So as we said, we talking about the data pre-processing. Data pre-processing, let's say, as we shown up in the slides, they have a here. I showed up with a standard scaler, min-max scaler, ordinal encoder, one hot encoder, and also some feature extractions that from Scikit-Learn feature extraction import dictionary vectorizers. And for the modeling and the learning part, so I'm just copy some toy type of code so that you can get an idea on how to call these methods to do with some learning modeling on that. For example, like we in this slides in this code we make blobs, and then we're doing the train and test the split, and then we call the model. So we already import from the linear model as GD classifiers, and then we fit the model, and we define the model and then fit the model, and then we make the predictions on that. So all those are just following with the same template. So that's why the idea is pretty simple, straightforward, but I know that the details might be very much details or if we want to really do some practical work. So we need some time to make a customization or to learning the details about the parameter list on that. Okay, so let's jump back to our slides. We want to mention about the last step of in the machine learning workflow. So that is evaluation, and after our training, after we make an evaluation of our model, so we want to deploy our model to the stage of the prediction stage, to running our model on the production data with the best model we already trained. So this is actually a problem of we need to consider about the model persistency. So after training the scikit-learn model, is usually desirable for us to find a way to persist, to keep the data for future use without having to train on the fly. So there are a couple of options that we can select. The one natural option is to use Pico. So Pico is Python's built-in library. So those are just come with the Python. It's commonly used for serialization process, and joblib are something that wrapper and extend for based on the Pico and extended the Pico. So using the Pico and joblib are pretty simple. So they come with some, you can save the data by dump method and then restoring the model by the load comments. So those are very simple or standard process to use for all the Python code to save the model and restoring the model. And if we jump back to our demo code, saving and storing a training model are just as simple as import the Pico and then dumps the model that we already trained, like a clf.fit classic, and then we can load the model and directly made the predictions based on the saved model on that. So the Pico can save as a string, all the model as a string. They can also save it to some disk like files, like say .pkl. That's usually the Pico file. And I believe that currently almost all the the deep learning or checkpoint files are in this .pkl. So those are actually the idea are the same as the Pico, but they may different from the Pico that's shipped from the internal Python. But those are the same idea to save everything in the serialization format on that. So back to our slides. So saving the model are not as simple as what it looks like in our example. So we may consider other things. For example, like in the Scikit-Learn, we usually define a pipeline. So to doing multiple works and define in like a workflow on that, and custom transformers. Let's say, remember that we can define our own transformers in the transformer object. So that cannot be serialized by Pico or joblib. So from the website, from the Google, I found that there are some third-party module that can save custom pipelines in stepwise. So those are pretty tedious, and I personally, I'm not very confident with that kind of a stepwise approach. So that's why in the documentation, so the Pico model are recommended to be deployed using containers. And because there's a lot of portability issues we need to consider. It's very dependent on different versions. I mean, sometimes the version, the slight updated change of the release version can crash the running of the code. So that's why the Pico model in the model persistency problem, and it's better to deploy that in the Docker-based like container or Singularity-based container to save the model and to make sure the portability issues not exist anymore. There's other issues for the Pico and the joblib. So because the Pico and the joblib by extension has some issues regarding the maintainability and the security. So I don't have time to explore the details about that point, but in the documentations of the Scikit-Learn, they provide a more secure format. They call it SKOps. So skops previously there's some extension libraries, but I think it is pretty good that they actually shown up in the documentation, official documentation in the Scikit-Learn. So it's better for us during the deploy stage or production stage. So we consider about the skops for the model persistency choice. Other thing that other issues that we need to consider about the model during the model persistency stage, so is we can export to export our model in other formats. So because the people are just assume that you just serialize all the Python objects, and it's not portable to other platforms or to other libraries, and then people just developed different like frameworks to define some common formats to make sure that the code or the model can be reproduced or can to have some quality control for different architectures and environment. So two examples are like Open Neural Network Exchange, ONX. So another one are the predictive model markup language. So when you see markup, so you may realize that those are the XML-based document. So those are to add more descriptive or very restrictive like a format restrictions to describe the model, to give the information of the model so that other platform or other architectures can use other than the development like environment. So I would say that those two are the options for the Scikit-Learn, but it is not very popular. So that's why I'm just I will not spend time on exploring this format, but I've just give you the two link about the Scikit-Learn ONNX and Scikit-Learn 2 PMML. So those are just some give you some idea on what it looks like nowadays for the Scikit-Learn community. So let's move to, I think we just finished the general review of the Scikit-Learn basic components. So let's review some interesting topic about the practical issues, or how nowadays, how can we use, as we meaning the data analyst or code developer, how can we practically use Scikit-Learn in our domain? So I want to discuss the two topics. One is deep learning versus Scikit-Learn. Another one is a brief review about the extension libraries for the Scikit-Learn. Okay, so everybody talk about the neural networks nowadays. So I actually got some questions from my previous talk that asking about what about like compare with the Scikit-Learn versus TensorFlow and PyTorch. Actually, the fact is Scikit-Learn also support the neural networks, and sometimes in some aspect they actually Scikit-Learn did a better job. So in Scikit-Learn, there is a module named neural network. So it provides, so far from the documentation you can find, it contains the three models, three neural network based models. So one is for unsupervised learning. They call it a Bernoulli restricted Boltzmann machine. So another two, the other two are supervised one. They call it the MLP regressor and MLP classifier. MLP meaning the multi-layer perceptron. So those are just the fully connected neurons and artificial neurons and connected each other, and then they can apply with some activation functions with the and then they can train using back propagation techniques to train. So everything are actually there in the Scikit-Learn. So I give you here in the slides, I give you the example on what the parameter list looks like for the MLP classifiers. So you can define what kind of solver to use in the MLP classifier. So those they use LBFGS, and those with the learning rate, and those with the they can give the size of the hidden layer sizes. So for example, like this one are 5 and 2, so that they can do with that kind of a size that specify the size of the neural networks on that. So LBFGS are actually optimizer used in the family of a quasi-Newton method. So different from the PyTorch and the TensorFlow that actually use the gradient descent method. So those are actually some quasi-Newton, like a second order of the optimization of, they call it optimizer. So you can also use the general optimizer, say SGD, like a stochastic gradient descent. And you can also use with the Atom. So I would say that by default, Scikit-Learn also use Atom. They call like a stochastic gradient based optimizer. By default, they will use the Atom as the solver on that. So alpha, let me check. Alpha, I think alpha is the strength of the L2 regularization term. So, and I believe that in the MLP classifiers and the MLP regressor both use parameter alpha for L2 regularization to avoid overfitting by penalizing the weights with large magnitudes. So, and of course, so you can see that it can only define very rigid, like maybe fully connected like neural networks. So it's not versatile or flexible as TensorFlow and the PyTorch. But I would say that it's much simpler and straightforward, especially whenever you're doing some early stopping. You will see that it will be much straightforward way to doing the early stopping. And also one important thing that, because I'm from engineering background, so I'm actually prefer to, I dealing with a lot of problems with we need to support the sparse data. And in the Scikit-Learn, so they have a direct support for the sparse data as input. So they save the memory a lot, I would say. And also they, one thing that they're doing much better than the PyTorch and TensorFlow is that they natively support partial fit. So the partial fit is became more and more important because the model becomes bigger and the data becomes bigger. So we may need to gradually learning. So as time step to get the more new data to yes, something like that. So that's actually a very important feature. I believe that in that sense, Scikit-Learn did much better than the PyTorch and the TensorFlow. So I actually form code snippet that I want to spend a little bit time to doing that, because I think this is this is a very interesting topic that we'd like to explore. Okay, so so you click the we can click with the third link to bring up the demo on that for comparing with the Keras or TensorFlow versus and PyTorch versus Scikit-Learn. You can see that it's pretty simple. Under the Colab, we just import the necessary libraries from Scikit-Learn for related model that we would like to use. And also they come with the Keras, with the TensorFlow. And also we have also they come with the PyTorch. I believe that I ran this, I saved those IPython notebook, I think some time ago, so that's you may get the different version of the PyTorch on that under the current Colab session. But anyway, so for here, we want to use a problem, example problem, that is a small text classification data. So this is the intent classification from a bunch of text sentences. The data set are mixed with in-scope and out-of-scope data. The in-scope meaning, so you can see the OOS or the other labels. So in-scope means the text that has the definitive labels for the intent, such as what is my balance, such and such, and it contains 150 intent. I mean 150 classes. So out of scopes is a special kind of intent labels. It represent some text content that may not be form a well-defined target label set. So that's sometimes it's called like out of a distribution problems. So so the total number of labels or classes would be 151. And then by doing the data preparation or pre-processing stage, we need to so those are we downloaded from some website, from some public site, and then we read the JSON file into the Panda framework, and then we use the count vectorizer. Count vectorizer are actually the count vectorizer are one of the models in the feature extraction.txt in the Scikit-Learn. So, and then we do the fit and the transform for both training, for the training data. So using the text and the label, and then we make the train test split for the data. And then we doing with the count vectorizer again for the training data with the encoders, and then to encode to make the transformation for the labels of the data for the training data. So all those, I want to say that all those are just done by the Scikit-Learn. So you can see that Scikit-Learn are actually a very powerful tool for that. And for here, I want to say that it's by default, Scikit-Learn X-Train are actually by those count vectorizer.fit. So by after output, they actually get not the dense data. They automatically get the scipy.sparse.csr matrix. And those are just the sparse format, sparse data format. And only Scikit-Learn can process with those sparse data. And then doing the comparison of the TensorFlow and PyTorch, they can only, I don't know, maybe somebody can teach me how to do that, but I didn't find any way to dealing with those sparse data in a simple way. So that's why what I did here is to convert this sparse data into the dense data. And then those are, you can see that those are just the shape are actually changed. So they have a different shape of the data. of course, size of the data. And then I did, so the next step is I did the multi-layer perceptron in implementation using Scikit-Learn. So you can see that Scikit-Learn are pretty straightforward. So that's a follow the standard template that we shown. So it's so those are the timing that we want to make some performance measurement. But you can see that we just define the model and running the fit, and then we make the predict. So all those are just the standard template. And for during the training, so we need to see, for example, we need to have those like early stopping. So that's why I implemented with some like early stopping functions on that. And then as simple as I think this is the simplest approach that I've ever seen, is we can, in the MLP classifiers, we just specify early stopping equals to true. So we don't have to save the previous step of that, doing some manual work to doing the judgment of whether it's stopped early or not. And those are the very elegant indeed. And we can see that there's we can do the same thing for using the Keras or TensorFlow. So in the Keras, we define the models as sequence, and then the layers with the dense. And so those layers are dense. So not to say that the data has to be dense on that. So they cannot process with SciPy's sparse data. And then they can do with the same thing for the counter vectorizers for the fit, and then doing the transform. All those are Scikit-Learn, and then we define with the data as the sequential to add the one layer of the one layer and another hidden layer, and define compile to using categorical cross entropy on that, and then we running the fit. So those are, I would say that Keras actually follow with the same, trying to have the same API or similar APIs as the Scikit-Learn. I don't know which one is earlier, but they follow the same similar API with the model name .fit, and then they get the predictions with the to select with the running with the predict, and then to collect the results on that. For the PyTorch implementation, it's take a little bit more work because relatively speaking, PyTorch is sort of like a lower level of API compared with Keras, or not to say compare with the Scikit-Learn. So, but I think I already shown up those piece of code in my learning PyTorch session or workshop. But at the quick review that you just generated with the data loader and define the neural network architectures by the sequential hidden layer, hidden activations, and then define the metric function, define the optimizers, and then training the model, training the PyTorch model for different epochs, and then to get everything blah 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 blah. So those are just basically those are just doing the same thing as the Keras TensorFlow, but they need some more explicit code implementations. And the interesting thing is we run some performance test. So for example, like we can run the Scikit-Learn, and then we can run the Scikit-Learn with early stopping, and then we can run the Keras, and then we can run the PyTorch. So those are running to see how long it takes finish the training for the training. And then we can checking how much memory that they used for 3 different libraries. So we have to install the memory profiler, and then we can mem it for the Scikit-Learn, for the Scikit-Learn with early stopping, and then run Keras, and then run the PyTorch. So those are just the results that I collected for based on these sections, based on the performance tests that we got those numbers of the times and the memories and the accuracies. And I use the so just the numbers, and I used a piece of code to illustrate the results. It's pretty interesting that you can see that for training, looks like PyTorch have a much better performance. So they takes the number here are the less the better. So we can see that it's a Scikit-Learn without early stopping, it takes longest time, but with early stopping, they just reduce a lot. And the Keras did the same thing, similar as a Scikit-Learn with early stopping, but PyTorch is the winner here. And interesting in the prediction stage. So predict time are the Scikit-Learn are actually just winged out of the prediction time. So you can see that Keras takes the longest time to make the prediction. And then the PyTorch, well, it's okay, but then not comparable with the Scikit-Learn, obviously. And the test accuracy, all four are roughly the same. So that means all four are doing the same quality of job doing the test. But you can see the memory usage. So Scikit-Learn and early stopping way better than the Keras and the PyTorch. I think that the reason is obvious, because they inherently using the sparse matrix, the sparse format save a lot of almost like a 2 to 3 orders of magnitude of the memory. So those are the strengths of the Scikit-Learn. So I think this results are pretty interesting. I got some part of code, some idea from website, and I did some of my learning, some of my coding myself, and I found I'm happy to share that what I'm findings here. Those are so I think those Scikit-Learn is pretty good for some tasks. So let's jump back to our slides. Deep learning and Scikit-Learn are not direct comparison, but also they can work together. So as we shown in the large language models, so those modern days, they have numerous exotic deep learning models, and large, in that sense, large neural natural language processing models can provide us with a very good starting point. I mean, in most sense, a lot of models are actually can be treated as a pre-trained or semi-supervised one, so that we can use the Scikit-Learn to work together with those they call it like a foundation model for especially for supervised fine-tuning. Of course, they can do with other works other than supervised fine-tuning. But in the example that I want to show you here, the idea, I don't want to show you the code, but it's a sort of long to load the transformer model and the BERT. But it's I think this is the model that I saw somebody using the Scikit-Learn work with the distilled BERT model, so that the Scikit-Learn can do in this workflow, they can do 2 parts in the workflow. One is the Scikit-Learn can provide a top classifier model, a classifier layer, to doing with the logistic regression. For example, like in this example, in this cartoon diagram, so we want to make a test like a how to say that, they can check whether this is spam or this is not a spam. So that's a logistic regression problem, typical. And they can, Scikit-Learn can provide it with the top layer, I mean, at the end of to do the classification work. And also they can define with they use the pipeline. You remember the model, the model selection, or in the meta estimator module in the Scikit-Learn, so they provide a pipeline. So they can use the pipeline to define all those workflows on that. So I think this is a very good example to show that the Scikit-Learn, even in the modern deep learning days, they can still have their position to help us to do a better work on that. Okay, so this is all just the basic Scikit-Learn. There are tons of extension libraries that expand the capabilities for the Scikit-Learn. So in reality, so we may need to import or to install and to work with to use the Scikit-Learn extension libraries for our problem. For example, like there are a lot of libraries that are adopting the Scikit-Learn functionalities. Basically, internally, they use some Scikit-Learn components. So for example, like for different data formats, autonomous machine learning, auto ML, and visualization, model selection, parallelization, and plotting, and of course for those Pico and those SKOps. So those are just the adopting internal functionalities from the Scikit-Learn. There are some library compatible with the Scikit-Learn interfaces, so they may re-implement the functions on that. And so there's some time series models like TS-Learn, SK-Time, deep learning with the Scotch. So they actually adopted the Scikit-Learn interfaces. They have other regression and classification, and they have decomposition, clustering. They are all not using the Scikit-Learn internal functions, but they have the same or fully compatible interfaces, APIs for the Scikit-Learn. So Eric, they type a message in the meeting chat. Thanks for the course over. I'm not sure what the advantage of Keras and Pyrus versus Scikit-Learn. They seem to consume more storage, computing power, and processing time. So in what cases would we use these rather than Scikit-Learn? I think this is a very good question. So the example that I used is just a very simple or maybe specific example that Scikit-Learn can give us that significant performance boost or advantage. In most cases, we like thinking about the PyTorch or TensorFlow. So they have more flexibility to define various or exotic structures for the deep learning problems. So many problems you cannot, or it's impractical to define with some fully connected neural networks. I think the art of neural networks, or the strength of the neural network, is that we, as an architect, we have those Lego pieces, but then the thing is, how can you construct some creative or efficient or exotic architectures from those Lego pieces, like say artificial neurons? And also, not to say that the specific structure of neural networks, they can have a different, they need different techniques to calculate. Say, for example, like if the layer is more and more, the neuron numbers is more and more, and then you may, well, you cannot training that by the simple implementation of MLP clustering or MLP like classifier or regressor. So you may introduce something like a convolutional neural network structure, or you can use some some ResNet structure to jump to connect it with each layers. And also you can have all those like a transformer, transformer in the natural language processing context. It's not for the Scikit-Learn transformer. It's a transformer architecture for the neural networks. So that's are actually impossible, or not completely impossible, but it's not ready to use for the Scikit-Learn. So that's why it's an open topic for the scientists or engineers for us to apply those exotic like neural networks or the power of those neural networks applied to some domain-specific scientific problem. I hope that makes some sense. Yeah. So I would say that it's in Python community, Scikit is short for the SciPy toolkit. Usually means an add-on package for SciPy. So that's originally Scikit-Learn developed for as a third-party extension library for the SciPy. So it's but I would say that it's a huge family for the SciPy library. So it's many add-on packages for SciPy hosted and developed separately and independently from the main SciPy distribution. So when you do search in Python package index with the Scikit, you will come up about like a 2,500 plus or 600 packages. So of course, the most famous one would be the Scikit-Learn, but there are most Scikit-Learn related packages, but they are just more than that. There are more packages that aren't related with the Scikit-Learn, but they use the site. You can see the Scikit as in their name. So I say Scikit op, Scikit sparse, Scikit image, Scikit stats model. So all those are just for bigger family. They are sister packages compared to the Scikit-Learn, but they are different thing. So I'm just saying that it's for us as the code developer or the data analyst to feel free to choose any tools and make those tools work together for our problem. Okay, so we actually just finished the discussion about the learning Scikit-Learn, and in the next Friday, I will just dive into some advanced topics on the performance issues in machine learning, and specifically, I will talk about how to make the computation faster and how to process the large data sets while using Scikit-Learn and at the same time using some similar Scikit-Learn techniques to handling with those high performance machine learning issues. Thank you very much. I think I will stop recording here. I will stay in the online for some time, and if you have any questions, please feel free to open your mic and then discuss with me. Thank you.